Hi, everyone. Thank you again for the invite. I'm very happy to be here. And yeah, as David mentioned, my name is Mimie Liotsiou. I am a senior research data scientist at dunnhumby, which is a customer data science company here in London. My PhD was on causal inference. I'm a computer scientist by training, and my PhD was on applying causal inference methods to, in that case, measuring influence when people interact online. And since joining dunnhumby a few years ago, initially as a side project, I was asked to bring causal methods to the company, upskill colleagues. So I did a lot of talks, workshops, and so on. And more recently, I've been working on this full-time as a member of the science innovation team. And some of that we're going to see today because I've been working. One of my main projects recently has been media measurement using causal methods. So some of the examples and things I'm going to discuss are going to be based on that. So for those of you who have not really worked with causal methods and graphical causal methods before, I imagine you will still have heard the phrase correlation is not causation, and that's because some correlations can be spurious. So you might observe a correlation between variable A and variable B that does not actually indicate that A is a cause of B. So that's a spurious correlation, and a well-known example of that is the study that found that countrywide chocolate consumption was positively correlated with Nobel Prize wins in that country. And of course, that's not something we can sensibly interpret as causation. We're looking at this, we're like, probably something else is going on. And indeed, scientists did a follow-up study where they adjusted for income per capita, and in that case, actually, the correlation went away entirely. So it was entirely explained away by income. And so I'll show you kind of this modeled as a graphical causal model or a causal diagram or a causal DAG, which stands for directed acyclic graph, which is a mathematical object, and it's really key in properly answering causal questions. So in a DAG, in a causal DAG, you have variables represented as nodes. So this here represents the question, is chocolate a cause of Nobel win? So an arrow from A to B means there's a possibly causal relationship between A and B. So A is a possible cause of B. So this is what we're trying to study here. Does chocolate consumption affect Nobel wins? And as I mentioned, some other scientists adjusted for income per capita. So income is a possible cause of chocolate consumption because the higher your income, the better able you are to afford chocolate. But at the same time, the higher the income per capita, the higher the tax revenue in that country, and so the better able the country is enabled to raise funding for education and research, so people then are more empowered to do good work and potentially then win Nobels. So income is a common cause. There's this common cause relationship, also called a backdoor path in graphical causal model terminology. And basically, we need to so-called block backdoor paths, and that's something that graphical causal model theory tells us. So it's indeed right that scientists adjusted for income. It's something that we should do. And in this case, the relationship went away entirely. So if we had kind of taken the correlation at face value, not done the causal analysis, we might have said, okay, cool, let's invest in encouraging people to eat more chocolate in the hopes that we're going to get more Nobels as a country. But then we would have found zero return on our investment, and we would have completely wasted our money because, as it turned out, it was income all along and not chocolate consumption. So we want to avoid such scenarios. We don't want to waste our investments, and that's where causal methods come in, to avoid this pitfall and invest in the right thing that actually has a good causal impact in the way we want to move our metric. Now, of course, the thing is that all standard methods in AI and data science and stats are only about correlations and not causation, no matter how much big data we have. So as I mentioned, these can be spurious. So our estimate is not going to be the isolated causal effect. There's going to be bias in it, and that's why we need causal methods. And this is something that at this point, is quite fairly mature. It's recognized. It's graphical causal methods are used in the retail industry. They're also used quite widely in the tech industry. There's lots of big companies that you can look up online and find in their tech blogs how they use graphical causal methods. A lot of them have even built Python packages and other open source tools for other data scientists to do causal analysis in this way. So it's a really exciting time for causal AI. And so, okay, when do we need causal methods? Well, we need to use them whenever we have a causal question to answer. So a question about cause and effect. And these questions often take the form of what is the effect or the impact of something on some outcome, some KPI, and there's some examples here. Other causal questions might take the form of why. Why have sales fallen? Why has this KPI moved? What are the drivers behind, or the levers, or the factors affecting some KPI? And other terms that are often used when people try to answer causal questions are incrementality, uplift, and so on, the things listed there. So really in business, often the key is, great, cool, you've built me a predictive model of sales. Great, how can I increase my sales? How can I move this metric? What should I do? What lever should I pull? And that's where the causal methods come in to avoid what happened with the chocolate and Nobel's scenario. You want to invest in the right thing that's going to move the metric in the right way, and not just invest in a spurious correlation. And so just taking a step back, really the key thing between the traditional data science approach and the causal approach is what this slide is going to talk about. So in the traditional data science approach, often we're interested in prediction. So we might spend some time looking at our problem, defining our problem, and then fairly quickly jump into, here's our data, great, let's select some features, and then use our favorite data science model and do estimation. And once we've done that, we also care about validation, the goodness of fit of our model, how bad or good the error is, and that's sort of the standard pipeline, which is fine if all you care about is prediction and correlations. But if you have a causal question, you need some extra steps in advance. So you need to really carefully define your problem by representing it in a causal diagram. So I have an example there. It's like a toy diagram that was produced, using the Dagity software, which is this free online tool. So this is kind of a very toy illustration of the problem of the effect of an ad on spend. So you go to Dagity, you define your variables, you say ad is my cause of interest, spend is my outcome of interest, and then you can think about what other causal factors might matter, especially common causes, and let's say, loyalty might be a common cause of why someone sees an ad and how much they spend. Similarly for time of year and for the brand of the product. So you model your data generating process and the causal mechanisms in the world in a DAG. Once you've done that, the next step is what tells you what variables you should be adjusting for from the DAG to isolate the effect of the cause of interest, and that's called the identification step. And so it isolates your causal effect from spurious correlations that come from other causal relationships in the world. And that step is automated, so Dagity does that immediately. There's other tools, like I'm going to mention in a bit, like the DoI library, that do this step. So once you've done that, these are the variables I should be including as inputs in my model, and these are other variables that I should not be including as inputs. So in this case, the three red things with the red arrows coming from them would be things that we should put as inputs into our model. So when you go to the estimation step and say you do regression, linear, nonlinear, doesn't matter, you should include as a variable the ad, whose effect you want to measure, and those other three variables. And then you do validation and so on. So this is really the key difference. And so the question is, when do we need to draw the causal DAG? Because there's different kinds of causal questions, there's different designs of trying to answer a causal question. So the key thing to kind of consider, and I've kind of put together this flowchart, is your treatment assignment random? If it's not, definitely draw the DAG and find the adjustment set to isolate the effect. If your treatment assignment is random, great, okay. Do you have a large enough sample of units over which you're randomizing? If not, again, draw the DAG. If you have a large enough sample, are you going to do an AA test? So this is pretty standard practice in companies that have an experimentation platform. A way to test if the randomization worked is a so-called AA test, and you can pass or you can fail. If it's failing, then you need to figure out why. So you're kind of back to having to draw the DAG to understand with respect to which variables are people getting disproportionately allocated to one treatment arm and not the other. So really, regardless of design, you are, in most cases, going to need to draw the DAG at some point of your analysis. And so we've covered drawing the DAG, we've covered the identification step. Now comes the estimation stage, and there's different methods you can use here, depending on what's most appropriate for your particular problem. I'm listing some over there. You can use regression, matching, propensity scores, maybe use your propensity scores to get inverse probability weights, double ML, difference in differences, and so on. So these are all great methods, and they're often, you might encounter them mentioned online in blogs about causal questions, and indeed you should use them, but they're not in themselves what makes your claims causal. You need the causal DAG and the identification step, and then these are all good methods for the estimation step. And just to illustrate a bit more how these methods might all work together in different kinds of causal pipelines, let's say we have again the question of what is the effect of this ad on spend. So let's call the ad variable X, let's call spend variable Y, our outcome. And so we'd start by drawing the causal DAG. Again, let's take the toy DAG from before. And then based on that, we do identification. And in this case, it was, let's say, these three variables that are our minimal deconfounding set. So the variables we need to adjust for. And let's call this set of variables Z. Now we take the Z and we feed it into our chosen estimation method. So one approach might be, great, I'm just going to do a regression. Linear, nonlinear, again, doesn't matter, whatever you think is best for your context. And you would regress Y, your spend, on X, the ad, and Z. So that's what you should regress on to isolate the effect of X. If your X, your cause of interest, is binary, as is the case, for example, in this ad example, what people often do is they match treated and control units, so they try to find similar treated units and similar control units. But what should they be similar in terms of? Well, they should be similar in terms of this minimal deconfounding set Z. So that's what you should match on. And once you've done that, you can compare the mean outcomes in the treated versus the control set. You can do very simply like a t-test, or you can do ANOVA, ANCOVA regression, whatever you want there. Now, with matching on the covariates in Z directly, what can happen is you might get hit by the sort of curse of dimensionality, where, especially if you've got a lot of categorical variables with several categories in each, it might get really hard to find good enough matches for all of those variables. So one approach that we also took in our study and on causal analysis of effects of ads is you can instead feed them into a propensity score model and kind of collapse them all into a single score. So basically, you have to create another model, and you can use, again, linear, nonlinear classification. So you can use logistic regression. You can relax the linearity assumption and do like a random forest or something like that, which is what we went with. And create this propensity score, which basically tells you the propensity or the probability of units to get treated or not, so to get the ad or not. Once you've done that, then you can match just on the propensity score, and there's various tests you can do to see, okay, is the propensity score adequate enough? And then, having done that, you can regress your outcome on the ad, on the X, and then you could potentially also regress on the Z to kind of have a more doubly robust design so that it's a bit more robust with misspecifications, either to your propensity score model or your outcome model. So there's, again, different ways to combine these methods. There's other approaches as well, and these are some just illustrations here. And finally, mindful of the time and that this is a short talk, I should just mention, again, there are some tools you can use for hands-on application. Dagity, as I mentioned, is an R package, but it's also a free interactive web tool, and it's really useful. DoI is a Python package that does graphical causal models. They have a lot of overlap in what they do, but also each one does things that the other cannot do, so I recommend looking into them. And as David mentioned, I did do this other more in-depth Data Science Festival talk. It's all online, and it covers both the theory of causal methods, statistical paradoxes that graphical causal models address and resolve, the jargon, the theory behind them, why these methods work. And it also covers end-to-end implementation in Python with the Python notebook. It's a question there that's studied is the effect of joining a loyalty scheme on sales, and all of the materials are online, so that might be helpful if you're interested to look at it. And if you'd like to look at more content from me as well, I've gathered various talks and links to various things I've done externally on my website. And yeah, feel free to get in touch, happy to have a chat. And I'm just going to leave you with these quotes. It's a really exciting time for causal inference and causal AI. More has been learned about causal inference in the last few decades than ever before. And it's always worth remembering that data science is the science of interpreting reality and not just summarizing data. Thank you so much.
Awesome, awesome, awesome. We're going to keep things moving. I think I'm going to take 2 questions, if there's questions, and then we have a short comfort break, and we're going to go from there. So where are we looking for questions? I've got one here. I'm sorry, he's much closer. I'm going to come to the back for the next one, I promise.
Hi, thank you very much for the insightful talk. As you mentioned, the most important thing is getting the DAG right. And personally, whenever I try to, apply that in my own setting, I find it quite hard to know what should be in the DAG, especially if the data is a lot more noisy and unstructured. Then at what point do you actually know, okay, these are the things I should put in the DAG, or my DAG is actually kind of complete? Because there may actually be like hidden confounders that you've never even thought about, or you just simply can't find in data, right? So from your practical experience, how do you design the DAG, and how do you know what is the right approach for that? Thank you.
Thank you. Yeah, that's a good question. So with graphical causal methods, there's this saying, no causes in, no causes out. So you can't do without a DAG. Even if you say, I'm going to do without a DAG, I'm just going to use some features. Implicitly, you have a DAG that guided those features while they're in your model. In building a DAG, basically boils down to your qualitative domain knowledge. So you can speak to domain experts, you can all sit in a room, have a few sessions with them, figure out, go through iterations of the DAG and try to be as complete in what is relevant in how the world works with respect to your question. Again, in the other talk that I pointed to, I go into this in a bit more detail. Basically, the DAG is quite flexible in that all it does is, the way you build it is you should include everything that you think might be relevant in terms of other variables and all possible causal arrows. So it's the omission of the arrow that's the strongest assumption. So when you say there's no arrow from A to B, you're saying A cannot possibly cause B. If A happens after B, that's a nice way to rule it out immediately. But that's really the strongest assumption. So if you start with a pretty fully connected DAG, basically you're saying, I don't know, I'm just going to throw everything in and then let the identification step work for you. So it doesn't impose a lot of assumptions in the way it works. In terms of, and then there are tests you can do to check your DAG versus the data, but then again, you need to kind of be confident that your data captures the underlying variables and reality adequately. So basically it's you need to do a bit more work, but again, no causes in, no causes out. You're going to be more confident that you are actually measuring the causal effect of what you think you're measuring. And the good news is you can do this once, and then you've done it, and any other time later on that you have to answer the same question or a similar question, the DAG is there. So you don't have to do it every single time you have a similar problem. And yeah, again, I'm going to refer you to my other talk. I have pointers to books, to academics, to more applied things, more theoretical things that have lots of guidance that give you the formal definitions a bit more. But in a nutshell, that's kind of how it works, yeah.
Amazing, amazing. Was there a question up here? Please.
I think the first question also mentioned something about unstructured data. So something like income and stuff, and I'm also an economist by trade. So those things I could think of. But nowadays, there's more and more data about something that I don't even know what to call it. It's like a video data or a voice data. Is there any advancement on that area with the causal inference?
I mean, that's kind of outside the causal or not causal thing, isn't it? It's kind of a broader data science question. But I mean, I'll give you an example from my PhD. So there, the data I was using to kind of measure influence in kind of whether certain topics get adopted in the project that people were working on. I was working with email data. So then you're trying to find, okay, what trait of these emails might matter. So you could model, you can try and measure the sentiment, you can try to measure the amount of participation. So you have to basically be cool, I have this video, what about this video might affect this person's decision process or the causal effect or all of that. And then you find ways to kind of, and there are many advanced ways to kind of automatically extract features and traits from unstructured data, yeah.
Fantastic, amazing. Can I have another round of applause, please?
Thank you.
Thank you, Mimie, thank you.